Today we're going to be working on simplifying radicals in this review. We have two rules that we're going to follow, which is going to be there can be no perfect square factors underneath the radical sign. And then rule 2 will be you can't divide by radicals. We'll have to rationalize. The last thing that we'll have is squaring radicals. So let's start off with number 1. We need a list of perfect squared factors. So I'm going to create a list real quick. 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, and this list keeps on going on and on and on forever. And we're getting this list by taking numbers and multiplying them by themselves. So 2 times 2 is 4, 3 times 3 is 9, etc., etc., etc. We're going to be looking for perfect squares inside of 12. So I can see that it's 4 times 3. The square root of 4 times the square root of 3, well, the square root of 4 is 2. And 3 stays inside the square root because it's a prime number. I'm going to do the same thing with 63. 63 is divisible by 9, and 9 is a perfect square. It's 9 times 7. So now I'm going to square root both of those because the 63 was in the square root. And I'm going to end up with 3 root 7. The square root of 9 is 3. Number 3 is 75, and in 75 there should be a 25. That's the largest perfect square. And then we're going to square root both of those individually because 75 was square rooted. And we end up with 5 root 3. 3 has to remain in the square root because it's a prime number. It doesn't have a match. Alright, 125, well, it's divisible by 5, so it's probably divisible by 25 because 5 times 25 makes 125. We're going to square root both of those, and we end up with 5 root 5. We're always looking for those perfect squares, and you can see that that's a part of that list. Now this one's a little bit more difficult because 80 is divisible by 4 and 16. So we always want to use the biggest perfect square, and that's our whole goal here. And notice there's a 2 on the outside, so I'm going to leave this 2 on the outside times the square root of 16 times the square root of 5. And if you notice, 16 times 5 is 80. And both of those are in the square root because I'm splitting up that square root into 2 different factors, 16 times 5. But the square root of 16 is going to be 4, so this is now 2 times 4 times root 5. And now we have to multiply the 2 and the 4, and we end up with 8 root 5. That is our simplified radical. Our last problem, number 6. We have a 3 on the outside of this square root, and we're going to break this root up into 2. So 28 is divisible by 4 and 7, so 4 times 7. And now we take 3 times the square root of 4, which is 2, times the square root of 7. 3 times 2 is going to get us 6, and then we have the root 7 because it's a prime. It stays inside that square root. Now, if you want, you can always go back 3 minutes and watch this again. Double speed does help with memorization and it helps with understanding. Hopefully you've been doing that. Okay, rule 2. We are not allowed to divide by radicals because we are dividing essentially by an unknown then. Radicals, in this case like root 2 and root 3 and root 5, they don't terminate and they don't repeat. So that means we don't really know what we're dividing by. And that's that's not the thing we want to do. So on number 7, we have 6 divided by root 2. So we're going to have to rationalize this. And the way that we're going to rationalize this is we're going to multiply both top and bottom of this fraction by root 2. And if you're looking at this, root 2 divided by itself is 1. So we're not actually changing this number, we're really just changing its appearance. To multiply fractions, we just need to multiply straight across. So 6 times root 2 is 6 root 2. And then root 2 times root 2 is root 4. And so this is the only time I'm going to do this. Root 4, or root 2 times root 2, is really just 2. So here's our simplified version, not fully complete. But this is 6 root 2 over 2. And from here, we should be able to simplify a little bit further by saying, hey, 6 divided by 2 is 3. So I'm going to reduce the top by 3, and then 2 divided by itself is 1. And you can write it like this, 3 root 2 over 1, but it's really not necessary. We don't need to divide it by 1. We can just write it as 3 root 2. Whole purpose, getting rid of the denominator's radical. And we did that. We accomplished it. We actually don't even have a denominator anymore. So, next problem, we have a root of 3 in the denominator. So we're going to multiply both top and bottom by root 3 because we want to get a perfect square. And we do that. Root 3 times root 3 is root 9, but I'm going to go a little bit faster and say, hey, root 3 times root 3 is just 3. The square roots are gone because when you square a square root, they cancel each other out. They're inverse operations. Root 2, though, times root 3 is going to get you root 6. Now I'm going to pause here and just talk about the root 6. This is really important. Root 6 is not divisible by root 3. They're different families of numbers, essentially. The root 6 cannot be divided by that 3. So we're just going to leave it right here. This is the simplified version of this fraction. Last but not least, we have the 7 divided by root 5. We're going to multiply both top and bottom by root 5 because when we do that, we end up with 7 root 5 over root 25. That's a perfect square. And we end up having our final form of 7 root 5 over 5. Now we can't really go any further than this because 7 divided by 5, they're both prime numbers. We'll just leave it as that. So 7 root 5 over 5. Go ahead, if you need to, you can always go back a couple minutes, watch this again at 2x speed or 1.5 speed. That really helps me. I hope you're trying that. One more thing that we should know is squaring radicals. And these are inverse operations, so if I square a radical or square a square, they should be canceling each other out. So let's write it. Square root of 7 times the square root of 7. Well, that's really the square root of 49, or just 7. On the second problem here, or I shouldn't say second problem, on problem number 11, we have 2 root 3 squared. And this time we have 2 different sets of numbers. We have a whole number and then we have a root or a radical. So this is 2 different types of numbers. And that means they're both going to be getting the square. So when I look at this, I think of 2 squared times the square root of 3 squared. We just discussed beforehand that when we square a square root, they cancel out. So I'm going to end up with 4 times 3, which is 12. But I want to analyze this in another way. If I have 2 root 3 squared, then I'm going to also have 2 root 3 times another 2 root 3. If we go back a little bit in years, we can talk about the commutative property, which means we should be able to move things around in a multiplication problem since these are all multiplying each other. And I would rewrite this as 2 times 2 times root 3 times root 3, which again gets us 4 times 3. Same thing. So there's a lot of different ways to think about this. We can use the laws of exponents if we want to use that, or we can utilize that idea of exponents and spread this problem out as 2 root 3 times 2 root 3 and write it as it should be with multiplication. Now I'm going to go quick on this one. Since there are 2 different bases, we have the whole number base and we have the root base. This is going to be 5 squared, which is 25, times the root 2 squared, which is just going to be 2, and that's going to get you 50. Now, on your paper on page 8, you have some practice problems. Make sure you get them done. If you have any questions, come visit me or another one of the teachers, and we will definitely get you squared up, making sure that you understand how to use radicals or reduce radicals in this scenario. I hope you have a wonderful day.